A modern skyscraper is essentially a giant thermal trap. Between the solar gain pounding against acres of glass, thousands of human bodies, and floors packed with running machinery, these structures constantly generate an immense, pulsing heat load. Standard air-based cooling relies on moving heat through air ducts, but air is a poor thermal conductor. To cool a skyscraper this way, the ductwork would have to be so large it would consume the building's usable floor space. Because water can carry over 3,000 times more heat than the same volume of air, industrial-scale cooling requires a transition from air cycling to liquid-based thermal transport. This is the role of the centralized mechanical chiller plant, a specialized system engineered to manage these high-density thermal loads. The chiller operates as a high-capacity heat extractor. It pulls thermal energy out of the building's internal water loop, lowering the water's temperature so it can be sent back through the structure to absorb more heat. This makes the chiller a thermal transport mechanism. It is designed to bridge the gap between the heat generated inside the building and the environment outside. This presents a strict thermodynamic challenge. Moving heat energy out of a building requires forcing it against a natural temperature gradient, so it can be rejected into the warmer external environment. To understand how megastructures remain habitable, we have to look at the exact mechanism making this possible: the four-stage vapor compression engine. We start with a closed loop of pipe, isolated from the building's air, containing a chemical refrigerant. We'll map its behavior on a pressure enthalpy chart. The first node is the evaporator, where warm return water interfaces with the refrigerant. The refrigerant absorbs the building's heat, boiling into a vapor and dropping the water's temperature. On our chart, this absorption registers as a direct increase in enthalpy, while pressure remains constant and low. That low-pressure vapor enters the compressor. Acting as the system's mechanical heart, it forcefully packs the vapor, drastically increasing pressure and temperature. This work appears on the chart as a sharp, curved rise. The refrigerant is now a highly pressurized, superheated gas. The scale of the building's heat dictates the machinery used here. Small to medium loads use scroll or reciprocating compressors, but heavy industrial applications rely on massive centrifugal compressors to handle high-volume flow. This brings us to the third node in the loop, the condenser. Here, the system executes the actual heat rejection. Hotter than the surrounding environment, the refrigerant sheds its accumulated thermal energy to an external medium, condensing back into a liquid. On the chart, enthalpy decreases while pressure remains constant and high. Finally, this high-pressure liquid reaches the fourth node, the expansion valve. The valve acts as a strict bottleneck, forcing a sudden, dramatic drop in pressure. This causes the temperature to plummet, priming the refrigerant to re-enter the evaporator and absorb more heat. We track this final phase as a steep vertical drop in pressure on the chart, closing the loop entirely. The physical architecture of the entire chiller plant is ultimately dictated by the condenser, specifically where it sends the heat it just collected. In this side-by-side comparison, the left side demonstrates an air-cooled architecture. Fans push ambient outdoor air directly across the heated condenser pipes to carry the thermal energy away. This method is straightforward but limited. Because it relies entirely on ambient outdoor temperatures to absorb the heat, it lacks the thermal efficiency required for anything larger than a small or medium capacity load. On the right side, we see the water-cooled architecture required for megawatt-scale industrial loads. Here, the condenser interfaces with a secondary external water loop. Water is far denser than air and absorbs heat much more effectively. This condenser water absorbs the heat and physically transports it away from the main chiller unit to a separate external structure, the cooling tower. Inside the cooling tower, the system leverages the latent heat of water evaporation. A small portion of the water is allowed to evaporate, absorbing massive amounts of heat and finally rejecting that thermal energy into the atmosphere. The entire water-cooled process follows a strict chain. Heat moves from the building into the chiller, transfers to the condenser water, travels to the cooling tower, and disperses into the atmosphere. Engineers select this complex, water-reliant architecture over simpler air cooling when the sheer volume of heat demands a more efficient thermodynamic sink. In this complete diagnostic model of the loop, we can map mechanical failures directly to disruptions in the thermodynamic cycle. A warning for high condenser pressure indicates a failure occurring precisely at the heat rejection node. If airflow is blocked, or water flow is restricted, or the condenser coils are fouled with dirt, the trapped heat cannot escape. The thermal energy backs up, physically driving up the internal pressure of the entire system. Conversely, low suction pressure points to a failure at the intake line just before the vapor enters the compressor. This low pressure means there is a lack of mass flow in the pipes. It points to a low refrigerant charge, a restricted expansion device starving the system, or simply a lack of actual heat load from the building to boil the refrigerant. A generalized symptom like poor cooling is usually a macro indicator of a heat exchanger failure, located in either the evaporator or the condenser. When water flow drops or heat transfer surfaces become insulated by mineral deposits, the pipes fail to conduct thermal energy, breaking the core thermodynamic exchange. Mastering chiller diagnostics requires understanding that all mechanical problems are ultimately disruptions to intended pressure gradients or heat transfer surfaces. Taking this conceptual loop and placing it into a modern mechanical room, we get the physical reality of a finely tuned centrifugal chiller. In this cross-section, you can see the chilled water and condenser water loops operating in close proximity, separated by a heavy steel shell. The plant operates in a state of delicate harmony. The compressor acts as the brute force driver of pressure, while the expansion device carefully meters the flow to guarantee precise temperature drops. Cooling large infrastructure is bound by one absolute constraint: maintaining an unobstructed, continuous river of thermal energy flowing from the building's interior to the final atmospheric heat sink. This raises the next logistical problem. Once the central plant has successfully extracted heat and chilled the localized water loop, how is that thermal capacity distributed throughout hundreds of floors in a skyscraper? The chiller serves as the thermodynamic beating heart of industrial infrastructure. It takes the basic physics of phase change and scales them up to form the foundation of livable megastructures.